Welcome. Previously in this series we have opened up the geometry. In this video we are going to take a look at meshing and the similarities and differences between Abaqus CAE and 3D Experience. So let's get started. In Abaqus CAE, if you follow the sequence laid out by the module listing, meshing is one of the last things to define before setting up the job. However, once you have your parts and assembly, there is nothing to stop you creating the mesh before any other operations. In this case, we have an assembly which is 2 repeat instances of the plate part and 1 instance of the rivet part. When we look at this in the assembly branch, we can see a context menu which has the option to make independent. In Abaqus CAE, we use the concept of dependent and independent meshes on instances. If an instance is dependent, as these are, then the mesh at the assembly is dependent on the mesh of the underlying part. Since the part is the same, that would mean both plates here would have the same mesh definition. This is what we will retain for the rivet, a dependent mesh on the underlying rivet part. For the plates in this example though, we will make them be independent. This means that the mesh at the assembly is independent of the underlying part mesh. Instead, controls can be set directly on the instance. This means multiple instances of the same part can have different mesh definitions, which is what we will do here. So we will set the plate instances to be independent. One note, in Abaqus CAE this is a binary choice. Either part instances are dependent or independent. It isn't possible to have multiple instances in assembly and then select only one of them to be independent. Note, you can see which instances are dependent and independent from the tree. Independent instances will have a mesh feature in the assembly instances branch. The dependent instances have no such feature because it is set at the part level and so is in the part branch. Now that we have set the type of mesh instancing, we will change to the mesh module and set up the rivet mesh. This is a dependent instance, so we need to make sure we are meshing the part, not the assembly. Here we will set a mesh control, so this is free meshed with tetrahedrals. Then we will assign a mesh seed size and generate the mesh. Going back to the assembly mesh, we can see the dependent mesh already. Since the plates are independent, we can set up different mesh definitions. So we'll mesh the top plate with a fine mesh and use a coarser mesh for the bottom plate. We'll use the same technique though for both of these and make it a hex dominant sweep mesh. Meshing these instances, we have our complete lap joint mesh definition. In 3D Experience, things are a little different. However, there are some similarities we will see. Here we will open the plate subassembly and then open the plate part individually. These all open as new tabs so we can switch between them at will. The first change we need to be aware of is that in 3D Experience we don't use modules to group together commands at a particular stage of the model. Instead, we use apps. In some respects, these apps are very similar to Abaqus CAE modules. So when we were in the assembly or opened the subassembly, the app, which we can see just next to the compass at the top of the window, was Collaborative Lifecycle. When we opened the plate part, this switched to Part Design Essentials. Exactly which app you open will depend upon what roles you have. Here at the part level, we wish to create a mesh. Part Design Essentials is an app that has commands for creating geometry. So instead, we will swap to a meshing app. We can swap apps by going to the compass and then selecting the app we want from the listing there. Structural Model Creation is the app with the mesh generation commands. We'll get an info message about the product structure needing an update. We will ignore that just now. Then we see a new dialog asking if we want to make a FEM based on a standard general purpose setup, or if we wish to create an empty FEM. As we intend to show all the steps needed in this video series, we will choose to create an empty FEM. Now this has done something different to what we are familiar with in Abaqus CAE. In 3D Experience, meshes and properties are grouped together in a separate branch of the feature tree. This branch is the Finite Element Model, or FEM. Here, since we're at the part when we create the FEM, it is a branch directly under that part, similar to the 3D shape and abstraction shapes. Conceptually, we can think of this as meshing a part object in Abaqus CAE. One of the first things a FEM needs is to know which geometry is intended to be meshed. We saw in the previous video that in 3D Experience there can be multiple geometries in a part, the 3D shape, which typically is the fully featured design geometry, and then abstraction shapes, which here are either the positive or negative halves of the symmetry cuts we are using as our analysis geometry. Here we will use the negative symmetry abstraction shape as being the geometry that this particular FEM will mesh. We will also give this a more meaningful name than the auto-generated one. Now that we have a FEM and we have told it which geometries it will be for, we can go to the Mesh tab and do a sweep mesh, which is a command in the stack that has partition hex mesh. In this dialog, once the geometry is chosen as the support, the display will update to show the source and target sides. We will specify a 0.5mm mesh size for the cross section and the sweep direction, as we did for the finer mesh top plate in Abaqus CAE. This gives us a FEM at the part, which is one half of the overall design geometry. We know that in the assembly the bottom plate is a rotated orientation of the top plate, so the matching side is the positive symmetry geometry abstraction. This is where we see another difference to Abaqus CAE. Just like with abstraction shapes, it is possible for a part to have multiple FEMs associated with it. We will insert a new FEM here and give it a name appropriate to identify the positive symmetry side. In this new FEM, we will choose the other abstraction shape to be the geometry to work on. We will also mesh this with a mesh size for the coarse plate in the Abaqus CAE model. Note, this ability to have multiple FEMs makes it easier to manage situations where you may need different meshes. If you're doing a detailed analysis of a part like a bracket, you may have a fine mesh with all the details in a FEM, then have another FEM which is a coarse mesh simplified representation of the geometry, so that in a larger assembly where you just need the load path, that analysis model isn't excessively large. Each of these multiple FEMs can point to the same abstraction shape or different abstraction shapes, and those abstraction shapes will reference the design geometry. So if the design geometry changes, that can ripple back through the abstraction shapes and into the FEMs for efficient mesh updating in iterations. Moving back to the subassembly tab, we can see the meshes displayed. We also see that the rotation of the bottom plate as the fine and coarse mesh halves are shown. One thing to note here, although these meshes are displayed, that doesn't mean that they would be used in an analysis of this subassembly. This is purely a visual indicator as the FEMs are displayed for the underlying parts in the assembly. If we wish to do an analysis at this subassembly level, we need a FEM at this level. So we will insert one. Note, at this assembly level, the context menu is getting too large to show the FEM directly. Instead, we'll insert a representation. This then brings up a dialog box where all the possible representations could be chosen. We'll find FEM under the simulation model options. This has created the subassembly level FEM. We will rename it as appropriate. This FEM has the same nodes and elements and property branches as we have seen in the FEMs from the part level. Instead of just showing and hiding, we need to define which geometries this subassembly FEM will work on. So we will drill down into the assembly part structure and select the appropriate symmetry abstraction shapes. As we move into larger assemblies, particularly of parts with multiple representations, the display can start to get cluttered. Hide and show from individual context menus can be time-consuming. However, there is a shortcut in the Visualization Management command. This brings up a dialog where we can use drop-downs to quickly show and hide different groups of entities. So we can hide all the shapes, show all the shapes, or just show the shapes which are contributing to this FEM that we're actively in. From the expanded feature tree, we can see that this is showing and hiding groups of entities with a single option. At the moment, we have seen that we now have the subassembly FEM, and we have identified which of the abstraction shapes contain the geometry we want to mesh. In addition to contributing shapes, we can also specify contributing FEMs. In this dialog, we can see that for each of the two parts we have, there is a note that there are two candidate FEMs which could be used. Right-clicking in these cells, we can bring up a context menu and choose which FEM to select for that part. So we'll select the negative and positive symmetry FEMs as appropriate. These then get shown in the graphics area. So this is analogous to the dependent instance in Abaqus CAE. We have a FEM at the part level, then we can choose to reuse that part level FEM in a higher level assembly FEM. If we have multiple instances of that part, they can all use that FEM. In 3D Experience, this is referred to as assembly of meshes. The assembly level mesh is assembled from part meshes using the contributing FEM. As we've seen, this is not as restrictive as seen in Abaqus CAE. There can be multiple FEMs in a part, so a coarse meshed instance and a fine meshed instance is possible with both those FEMs in the same part. In addition, parts do not have to be dependent or independent. During the contributing FEM setup, you can choose some of the part instances to use an existing FEM. The other part instances would then be meshed at the assembly FEM level. Finally, this assembly of mesh approaches isn't limited to using part FEMs. Sub-assembly FEMs can also be used. Here, if we go back to the top level assembly and create a FEM, the contributing FEMs dialog shows that the plate parts have two candidate FEMs that could be used, but the sub-assembly also has a candidate FEM that could be used. This assembly of meshes approach can work very well if in your organization there are analyses done at various levels of the assembly, sub-assembly part structure. Instead of needing to rebuild a mesh at each of these different levels, the FEM can be created once and reused as needed by other analyses. The other approach in 3D Experience is mesh of assembly. This is where you mesh the geometries at the top level FEM for where you are. Essentially, this would be analogous to independent meshes in Abaqus CAE. The part level mesh on the plate was essentially like this. Here we will do this for the rivet in this assembly. The mesh of the rivet will only exist at this top level assembly FEM. This is convenient for easily seeing in the tree what is meshed. However, this does mean if we wanted to later do an analysis of the rivet only, that a new mesh would need to be generated at the part level. Parts and sub-assemblies can't reuse meshes from higher level assemblies. Both approaches have their advantages and disadvantages and can be mixed and matched in the same assembly. So the assembly of meshes for the plates and the mesh of assembly for the rivet. Hopefully this has shown that although 3D Experience uses different terms and the implementation is different, the existing knowledge you have from Abaqus CAE of dependent and independent meshes can help when working in the platform. The concepts are not identical, but they are similar. Here we've demonstrated the different approaches to give you an overview of them. For the rest of this analysis though, we will use a mesh of assembly of the overall lap joint. So we'll create a new assembly level FEM and quickly mesh each part. This will keep everything at the same level so it is easier to see. Thank you for your attention.